screen. So last time we went through the vectors. So this time we will do the measurement of little g. So we can do together. So basically, measurement of little g. G is, so we know Newton's law of gravity. So F equal to G m1 m2 over r squared. Where so this measures the gravity force between two objects. Let's say one is moon, one is Earth. So okay, let me see what's in the chat. Would get point of view a lab was submitted an hour or two late. It should be okay, but yeah, just try to submit it like on time. Okay. So so like the mass one is moon. The second one would be the Earth. So the r is the distance between the two planets. So this is how we measure the gravity force. And then we also know, let's say this is for what the example I just gave you is for the object from the planet, right? But let's say, because this law applies to anything. So let's say when we stand on the Earth, and so this m1 will become to our mass, and then m2 still the mass of the Earth, and the r squared is the basically between the center of the mass of ourselves to the center mass of the Earth. And so we can use this equation, right? And also when we do the measurement, when we measure like the weight force, let me see, I let people in. So F equal to mg. So okay, sorry. Any questions? Okay, maybe accidentally. Okay, so we know F equal to mg. So we equal them together, we can measure g, right? It's because m will be cancelled a lot, and then g will be gme over r squared, right? So far you know how we do the rationale, right? So basically, first we want to measure the gravity. So based on like the person and the Earth. Angel, you have any questions? If no, I'll mute you. Okay. So then we can also measure the weight force F equal to mg, and we put this because this is how we measure the force, and so the weight force is like how much you weight, and also because you're standing on the Earth, that the gravity make you basically produce this weight force. So this two should be equal. And then when okay, I need to mute someone. Okay, so when these two are equal, then you can find the equation of little g. You can calculate what g equals to. So basically, it's the universal gravitation constant g, and me is the mass of Earth, and re is the radius of Earth. So here they neglect the half height of a human because it's so small, so little compared to the radius of the Earth. So this is how we calculate little g. And when so since you have this equation, so we will just play around with the m, r, and other stuff. Then we can see what can affect the little g. So if you open the link for the simulation lab. And then, so the first one is to measure, okay, so let's see. So you can begin. This is better. So begin, then the ball of screen, click the ball on the top of screen to change ball characteristic of the choice. Oh, here. Okay, so now this is about the mass, the radius, and the ball materials. So you can change like the radius up and down, the mass. Can you change the mass? Oh, you can. Oh, because you can change the material, zinc and copper and gold. So because we know the different materials have different density, so rho times v, which we can calculate by the radius, right? It's 4/3 v cubic, and we can calculate the mass equal to rho times v. And then, so you can basically play around with the radius and ball material. And you see, then what's next? You can choose the name of color of planet, record this information in table 1 below. So basically, I think they want you figure out the planet name, and this is the ball. Okay. So this is the planet. So you can change the radius, the mass, and the planet color, and the density is already given here, and the planet name. So you can always play around and put the planet name here. This is under the planet button menu, and then you can record the mass, radius, density, and then what you're gonna do is imagine you're, let's say, Kobo, you're on this planet, and you zoom in. So now in Kobo, and the ball, you just cite the materials, the characteristics for the ball, and then we need a ruler. You click a ruler, so the ball is here, like 2 meters. So here's the unit, and you click drop. So basically, okay, so this is the time, the second. So 1 second, 2 seconds, 3 seconds, 4 seconds. Barely 4 seconds. It's maybe 3.8 seconds. The ball start dropping, and then reach to this point, which is 5 seconds. So the ball reach to the ground. So then you can calculate the velocity. The speed v1 is 0. V2 is here, you can read. Let me see. Oh, you click this one, sorry. I forgot to mention, when you have this little graph, you click this one and you will see the units on the X, Y axis, and you can see the numbers. So let's say, so this one, when the ball starts dropping, it's like 1.8 second. And so the initial speed is 0. We know, we can read it from here. Its initial speed is 0. And the final speed is about 6, 7, maybe 7. We can read it as 7. Then you put it here, and also the average of speed. You can take the average speed, and time 1, time 2 is when it starts to record. So this is time 1. So it's basically 1.8. This is time 2, and time average, right? So you would do 6 experiments for 6 planets, and then you keep the record here, and then try to plot a graph of the average, which is the average here, versus t average. Determine the slope of this graph. So can anyone tell me what does the slope mean here? What does this slope of the graph tells us?
The acceleration.
Yeah, that's correct. This is acceleration. Acceleration is also known as the little g, because this is like a free dropping, right? So this is basically asking you to plot a graph to figure out the acceleration. And then you plot a graph applying the mass versus applying the radius. Determine the slope of this graph. Let me write down something. Actually, even I read here, but it's the answer for the 13, question 13. So we know later G equal to this gravitation constant times m Earth and over r square, right? R square. So they want you to plot a graph of the mass versus finding the radius. So basically, what you want to do is mass over r square. R square, which is supposed to be g over g. If you do the equation, let's say if you divide it for this equation, you divide it by the capital G, then it should be m over r square and over equal to g over capital G. And then this should be the slope, right? This is the slope. And they ask you what is the significance of slope times g. So the slope times g equals to, so g over capital G and times g. So it's supposed to be it's supposed to be g, right? So what happened to acceleration due to gravity on planet as it increases, it becomes larger. So when the gravity on the planet becomes larger, so what happened to the little g? So okay, so gravity means like a so you can see from the original equation. Okay, I should stop writing this from here. Here. So if we see the gravitational, so this is constant, and okay, I think I should. So we can use this one. When the gravitational gravity become larger, that means the weight force become larger, right? And then because the m is like a physical property you cannot change, that means the acceleration will become larger, right? So this is when the gravity becomes larger, the acceleration also becomes larger. So yeah, so you basically fill a 6 planet here and then do the measurement and keep your record here and do 2 plots. So here I have I want to remind us. So when we do the graph, let's say A versus B or X versus Y. So normally you have the first one, V average versus T. So basically Y versus X. So you will do the first one will be on the y-axis, and the second variable should be on the x-axis. So this is how you plot. I will show you one example. This one should be 10, 8, 6. So when you plot, so you select them and then you insert and then scatter. Scatter, what I prefer is to this one. This one basically shows you the scatter with smooth line and the markers. You can see here. So this is X. This is Y. So basically, you can do this, and you take a screenshot, or you just save as a save as a template. Save as picture. You can save as picture and insert it in your Word. This is how you do the plot. And yeah, this is for the first part. Any questions so far for the first part?
No, I think it makes sense.
Thanks. So the second part is to explore acceleration due to gravity on planet with same radius but different masses. So when we have the so then we have to change one variables. Okay, when you click this one, it just will zoom out, zoom in, and when you click it one more time, it zoom out. Okay, so then you click reset, and then you can change the balls, change the planning. Let's say what they want us to do. So planet and decrease the mass. So we basically change, zoom out first, and the planet. We change the mass, decrease the mass and radius to minimum possible. Decrease the mass and radius. This is minimum, and the mass is minimum. So those are minimum values. And then click zoom in. So we're now on the planet again. What's the difference between capital and little g? So the little g is the acceleration. So you see, Fg equal to mg. This g is the acceleration, and the capital G is universal gravitational constant. So it's a constant. G is the acceleration. So for, let's say, on the Earth, little g is also constant, but it just because it's all fixed. Because g is fixed, me is fixed, r is fixed. So that's why g is fixed. But originally, g is fixed because of the capital G is fixed. Thanks. Okay, should I erase this? So if you wanna have any question, you can always after I post the recording, you can always look to watch again to see which part you're missing. Basically, in the class, I will cover all the questions and try to lead to the discussion how we get the answer. Okay, go back to this one. So now we zoom in already. So we want to have a ruler, and then place the ball at 4.5 hertz. So I think I just click here 4.5. This is 4.5. So you basically what I did was just click the height of the higher level of the ruler, so the ball started moving up. So click draw to begin the first round experiment. Drop. The ball to start dropping, and then click the grid on the bottom of the red screen. Record data for V1 and V2. So now if we click this grid, then we see here we can read from the graph like what V1 is 0, V2 is 1, 2, 3, 4, 4.8, I guess 4.8 meters per second. And then we take we record all the data V1, V2, V average, and T1. Okay, let's see what we define T1 and T2. Record data for T1 and T1. Where's the T1? So this is T1. Oh, this is V1, and this is T1, and this is T2. This is V2. Let me see. Click reset. Drop it as V2. Oh, I guess. Oh, actually, I think here they want you measure 2 times. Another wrong experiment. Same planet and we decided. So basically, so V1 and T1 is one batch of experiment. So they default the first initial velocity is 0. So when you do this, you run twice. So the first batch is you record V1 and the T1, which is like V1 is 4.8 and T1 is remember here T1 is a little bit tricky. T1 is not 2.5. T1 is from here to here, so which means 2.5 minus so T1 equals to 2.5 minus 1.2 0.6 second. This is how we calculate T1. And so you take 2 batch, then record each data in V1, T1, and V2, T2, and take the average. Then click reset to zoom in. Zoom out. Then reset and zoom out. Click planet to increase the mass by 1 upward arrow click. Change the mass. So change the mass 1 up. Record the name of planet, mass, and density in table 2. So you basically measure, record the mass and the density. When you change the mass, the density automatically changes. So you don't have to calculate. Just record here, and then you do and zoom in again. And the ruler. So 4.5, and then click drop. You measure 2 times. The first time, so this is the first time you measure. So you can record the V1. V1 is 5.1, and T1 will be 3.6 minus 1.8. So always remember, always this part you care about. Do not include the time from the beginning, okay? And then you do a second batch. You click one more time and reset. And drop again. So you record the second batch of data in V2 and T2. Okay. So now you can see you can measure this time and take average velocity and the time. So basically, and then after you're done this is basically this is one mass of a planet. After you're done this, you move to the next one. So what you're gonna do is to reset again, zoom out, and change planet. And you click one more up downward arrow. And then you start zoom in, ruler, and drop. So this is how you do this. You collect the data for how much they want you to do. You want to collect 6 different planets with 6 different masses. And then you collect the data of velocity and t. So then you have to answer some questions here. So when you increase the planet mass by maintaining the constant radius, you're in fact increase the planet's density. Okay, let me show you how it works with that. So now we keep the radius as the smallest radius, and then if you say remember that density is 2984, and if we increase the mass, you see the density will increase because so because the mass equal to rho times v, v equal to 4/3 r cubed. So if the r doesn't change, v doesn't change. V doesn't change if mass increasing, then the rho has to be increasing, right? So this is how the math behind it. So they ask you, what effect does this increase density have on average time for the ball to fall through the 4.5 meters? So when, let's see, when the mass is increasing, that means, remember we have another equation for the little g equal to g m. So when m is increasing, and little g will definitely increasing. If the acceleration is become bigger, that makes the ball fall even faster, right? So basically, when what effect does this increase in density? So when density is increasing, the mass is increasing. That means the acceleration is increasing. So that means the ball falls faster. So this is for the first question. And plot a graph with plot a graph with let me clean this screen, make it less messy. Because everything will be recorded, so you can always check on the video. I basically cover everything in the video. If you have any question or you don't understand, you get confused about certain problems, just watch the video. Then you can get a better sense. Okay, next one, plot the graph V average versus T average. Determine the slope of this graph. So because when we do the average, okay, I want to remind you guys, when we do the average, so this one, you basically get 1 point. Get 1 point, how do you do that? You just make an initial point of 0, 0. So let's see, drawing. So let's say average is maybe 3 meters per second, and the t average is 3 seconds. So it would be like this here. So also 3. And then when you do, how are you able to plot a graph? You just take the initial point and then do this graph. Oops. because when we take the initial, when we do the measurement, the velocity initial is 0, and the t we measure, we take it as 0 because here when we measure the t, it is the absolute value of t. Zoom in. You can see here. So when I do measure the t, I didn't measure from the beginning, right? But I measure from here to here. So that means the time, when they measure the time from the beginning when the ball is dropping, and to the ball finally drops. So you just remember to include an initial point of 0, 0. So for question 10, 0, 0, to include in the graph. What is the name of such a body which is so dense that it's difficult or impossible to escape from its gravitational force of attraction? So basically, that is that absorb everything. So what is this planet? You guys know? Let me see. Yeah, that's correct. This black hole. And check accuracy of your data point in graph producing table 2 by using linear equation motion. Okay, we want you to verify your data. So how many, let me think. So basically in here, when you plot this graph, when you change the mass, then later J will change as well. So basically you can plot you have 6 values, right? But you just need to plot one of them. You don't have to plot the 6 together in one graph because it doesn't tell me anything. It has no physical meaning. If you plot all these points together, it has no meaning. You only plot one, include the initial point. That should be good. So when you check accuracy repeat point table to linear by using linear equation of motion dy. So dy here is 4.5 meters, right? VIT average initial velocity is 0, and G planet at T average, you know this T average from this graph, from this table, T average. And then you calculate the G planet. So you can put the G planet here. And then it just help you to verify, because you already have 6 points here, help you to verify the slope, because you're gonna calculate the slope in this equation, in this question as well. So you can verify if you can get the same slope, the slope same to the acceleration in planet. Does it make sense?
Makes sense to me. It makes sense.
Thanks. And then you finalize your lab report. Any questions so far? If you have any questions, so you can just rewatch the recordings first, and then if you still get confused, you can email us.
We went through pretty quick, but I think that the direction seemed clear enough.
Okay, thank you. Yeah, that's pretty much for today. I'm sorry I was little bit. Let me see. Stop sharing.
Thank you for your help.